Right, kia ora all. Here I am back with the last question in the 2024 TGC Level 2 Chemistry Derived Grade Exam for Chemical Reactivity. This is the last question on acids and bases, question 3. Right, the first question, complete the equations to show the reactions of nitric acid and ammonia. So we do have to know what nitric acid and ammonia are. Hopefully this little word here gives away this one. This is a strong acid, so we need a single arrow. And remember, acids are donating their protons, so I'm moving an H and a positive charge. So this is going to end up with NO3 minus plus H3O plus. You do need to get those charges right, so take care with those. Ammonia is a weak base. You did need to know that. It is weak, so we've got the equilibrium arrow. It is a base, so it accepts a proton. So we move our H and our positive charge onto the NH. So we get NH4 plus OH minus. Again, be careful of your charges. Okay, calculations. So we've got nitric acid and a pH. And from that pH, we have to calculate both the hydronium and the hydroxide ion. So given that we've only got a pH, we need to know that we can calculate the H3O plus by doing 10 to the power of the negative pH. Okay, so I am going to go shift log negative 1.42 equals, and that gives me 10 to the power of negative 1.42 equals 0.0380. And this is an answer, so I'm going to leave this in 3 significant figures and give a unit. Oh, sorry, 3 significant figures and a unit. I was stuck on my calculator. Once I've got the H3O plus, I can use this, the concentration of H3O plus times, OH minus that should be, equals 1 times 10 to the negative 14. These equations are in your resource booklet. So here's my H3O plus, so I'm going to put that into here. Okay, so 0.0380 times OH minus equals 1 times 10 to the negative 14. So really another way you can remember this is that the concentration of one of them equals 1 times 10 to the negative 14 divided by the other. Okay, so let's do that here. And that gives us 2.63 times 10 to the power of negative 13 moles per litre. Let's just do a check. It's an acid, so I would expect my concentration of hydronium to be a lot bigger than my hydroxide. So that makes sense. That's 10 to the negative 13. That's 10 to the negative 2. Right, next calculation. Calculate the pH of potassium hydroxide. So that's a base with a concentration of 0.175. Right, I need to know that's a strong base. Therefore, it's fully dissociated. Therefore, because it's a base, if it's fully dissociated, then its concentration of OH minus is equal to that. That's an assumption I need to make, fully dissociated. So once I've got the OH minus, I do want the pH. I can't calculate it from that, so I need to go 1 times 10 to the negative 14 over the OH minus. It's going to give me the H3O plus. So let's do that first. Divided by 0.175 equals, that's going to equal 5.714, blah, 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 times 10 to the negative 14. And now I've got the H3O plus, the pH equals the negative log of the H3O plus. Right, so I'm just going to negative log that. And I get 13.2. I'm just going to do a double check. That's a strong base. That pH looks good for a strong base. Okay, and over the page. Last question, but it is a biggie. Real big question here. So we've got 3 substances, and we need to talk about their electrical conductivity and the pH with reference to the concentration of species and balanced chemical equations. Pretty standard question. So let's start by figuring out what these things are. So you can either remember what they are or you can use these numbers to help you. So obviously this is basic, and this is acidic. This is obviously not a strong acid. Hopefully you've remembered the pattern that all carboxylic acids are weak. Added to that, to remind us, weak things are poor conductors, right? So that's going to help us remember that that's a weak acid. This is a base. It's got a very high pH and it's a good conductor. So that's a strong base. This here, pH is basic, but not very basic. So you might think it's a weak base, but it's a good conductor. So weak things can't be good conductors. This is a basic salt. All right, so we are going to start with equations. We are going to do equations, we are going to talk about the dissociation, and we're going to link that to the 2 properties. So I'm going to start with the weak acid. So CH3COOH plus H2O goes to CH3COO minus plus H3O plus. Even getting that will give you a little achieved. All right, so we are going to go CH3COOH is a weak acid, therefore partially dissociates to form a low concentration of products. As the products are both ions, CH3COOH is a conductor, contains moving charged particles. I'm not going to write that again. Ions, but it is a poor conductor as the concentration of ions is low. H3O plus is a product, therefore the concentration of H3O plus is greater than OH minus, and therefore the pH is less than 7, 2.87. Its pH equals negative log of H3O plus. I could put in there, it's a weak acid, so the concentration of H3O plus is less than a strong, therefore the pH is higher, but it doesn't really ask for that. But just in case, strong acid of equal concentration. Just in case they ask you that. Okay, that's the first one done. Second one I'm going to do is my strong base. So this one sometimes trips you up. This is a strong base, so it fully dissociates, and we actually put water on the arrow there, because if you put water down here and you start to try and accept protons here, you're going to have some weird things happening. So you do have to try and remember that. Single arrow, strong, but the water is just splitting the ions apart. So again, NaOH is a strong base, therefore fully dissociates to form a high concentration of products, as the products are ions. The high concentration of ions means NaOH is a good conductor. See how I am linking specifically for conductivity, so I'm not trying to mudge them all together. OH minus is a product. a high concentration of OH minus means a low concentration of H3O plus. As OH minus is greater than H3O plus, the pH is less than 7. Sorry, greater than 7. Sorry, wasn't thinking. And that is 13. Okay, so let's go back up to here, and now we've got our last one, which is our basic salt. So we've got CH3, COONA, and our first thing that happens is that splits up into its ions. So CH3, COONA is a salt. It fully dissociates into a high concentration of ions, CH3, COO minus and Na plus, therefore is a good conductor. The CH3COO minus ions react with water as follows. CH3COO minus, so this is going to be our weak base. Weak, so I do my equilibrium arrow. And we need to, if it's a base, it needs to make OH minus. So the CH3COO minus reacts with water in a weak equilibrium, accepting protons to form OH minus. The concentration of OH minus formed is low due to the weak equilibrium. Oops. Therefore, the concentration of H3O plus is still lower than OH minus, but not as low as the strong base. This means we see a basic pH of 8.91. I said that. Yeah, good. Compared to NaOH, which produced more OH minus, therefore a higher pH. Something like that, just to compare those two. And then I think that one's done. All right. Hope you did well. Hope you studied hard. And if you didn't, you've still got a chance before the end of the year.